Well, welcome everyone to this a little bit unusual way to do class here today. I'm away at a conference, or I will be away at a conference when we would normally have class. So that's why we're doing class through this recording. So today we will talk a little bit about course evaluations, which are coming up. We will finish logistic regression, and we will start multinomial regression. With respect to save our stats, please remember to if you choose to do so, write a letter to the Board of Regents. Again, you can see my LinkedIn, you can see my Twitter posts, you can see my Blue Sky posts about exactly who to send it to, suggestions about what to write. And once again, December 5th is the Board of Regents meeting. Testify if you think that it would help. So, just also as a reminder, project number 3 is due on Wednesday, November 26th at noon. Please email it to me like you would normally. Email it to me as one group. It just might take a little bit of time for me to get back to acknowledge you that I've received it. So please be patient. Okay, so I want to talk a little bit about course evaluations. And let me get evaluation spelled correctly. So we're going to do 2 different kinds of evaluations in this course. The first is the usual kind that are available through Canvas. They are due December 13th. So to access them, just like you would with most other courses, let me actually come back up here. Oops, actually I got to the wrong part. Excuse me. So let's go to the home on Canvas. Now, if I come over here or come down to instructor course evaluations, that's where you'll be able to access your course evaluation, usual form, when it becomes available. Now, with these course evaluations, please note that in normal circumstances, these evaluations do really matter. It is the only way that my department has to evaluate my teaching, so I would really appreciate it if all of you take the time to complete the evaluation and be honest on it. If there are certain things that you really like about this course, such as the notes I put together, the R programs, the videos of our courses I put together, the website, please indicate that you like that stuff. Because again, in normal situations, those who would read my evaluation would see that, oh, yeah, a lot of the students really like the fact that Chris records his classes. Maybe I should encourage my other faculty to do that. That can actually happen. So if you like some stuff, please make sure you do indicate what you like. Now, there's a second type of course evaluation that all of you need to do. It's an evaluation form that I put together and basically made like a quiz/survey available on Canvas for you. So this would be like our other quizzes that we've had in the past. You are required to complete it, and I'll talk a little bit more about that shortly. And it's worth 5 points towards your overall quiz/project grade. Do note that this quiz/survey is anonymous. So if you actually would go into all the settings and stuff, I've actually made sure to indicate that where you see highlight in yellow, that indeed that these quiz/surveys are anonymous. This survey/quiz is due Wednesday, December 3rd at 5 p.m. It is okay to repeat comments that you've done from the other evaluation. In fact, I encourage it as well. Now, the quiz, as I said, is worth 5 points, and there's 9 questions. Unfortunately, I had problems constructing the quiz/survey, and so you're going to see that it actually looks like it's worth more points, but I will make sure everything is actually scaled to 5 points. It's simply, if you do it, you get 5 points. If you don't do it at all, you get 0 points. Okay, so let's go ahead and take a look at that quiz/survey a little bit more. Let me actually get to quizzes. So you'll be able to access on the normal quizzes webpage. Go to the bottom here, you see course assessment, quiz/survey. And let's just do a preview. Okay. So Question number 1 is the most important question of all. It is, I will be answering the remaining questions. If you say yes, well then move on and answer the remaining questions. If you say no, you can stop. That's completely fine. But you have to do question number 1. And if you do it, you get the 5 points automatically for this. You don't have to do anything else, even if you indicate that you will. It's just this particular question is worth the 5 total points. Okay. Now, hopefully you will take the time to do the rest. So let's go ahead and take a look at it. So tell me, what grade do you expect to earn in this course? What grade would you give this course in terms of the overall, let's say the material, what you've learned and stuff? Question 4 is, well, what grade would you give me as an instructor? And then number 5, we get into some questions about things that I would find useful so that I can improve teaching this course, and hopefully I will, teaching this course again in the future. So tell me, what were some aspects of the course that you think would be good to continue for future semesters? So if you think you like the videos that I post online, okay, put that down. Question 6. What were some aspects of the course that you think could be improved upon for future semesters? I want to know. I want to improve what I do. Okay, next, question 7. So I often teach many of my courses using a blended/hybrid approach. And I obviously didn't do that this semester, but I'm interested to hear your thoughts about if you would like this course to be taught in that manner. And so that's the purpose of this question here. So to give you an idea of how our class would look like in a blended learning format, basically what students would do is watch about approximately 1.5 hours of videos each week on the course material outside the classroom. So these videos might be 20 to 30 minutes long, and you might choose or you might have to watch like 3 to 4 of these videos. And these videos basically consist of me going through the notes, much like I did this semester in the classroom itself. Now, by doing that stuff outside the classroom, that gives me an opportunity of doing other stuff inside the classroom that we did not get to do here this year. And so our class would normally meet only on Tuesdays during the semester. And during the Tuesday class sessions, we would begin with a question and answers portion involving students who would ask questions about things that maybe were not necessarily clear in the corresponding videos. Now, the remaining portion of class time then consists of me reviewing material that I know that students can find difficult. Also going over additional data applications and examining projects and tests in more detail than I would normally because of time. So there's a number of things that we would do extra to help you learn the material, but it wouldn't mean that you would be responsible for learning more material. It just helps. This format allows me to center in on stuff that I know students have problems with, and also allows me to do additional examples. So the key is no new statistical methods are introduced during class time. That's on Tuesdays. Then on Wednesdays, students take every week low-stake quizzes, similar to the quizzes that you had at the beginning of the semester. Then on Thursday classes, what we would do is typically we would still have the classroom open, but it would be optional for you to come. It's almost like an office hours time where you come and ask me questions. You could get together with your group members and work on your project during the Thursday class periods, and I would be available to answer any questions. Another thing that we would do on Thursdays too is to have our regular tests during the semester on Thursdays. So with that as background then, tell me, which would you prefer, a blended or the current format for our course? Question 8, if you'd like to provide additional comments regarding your blended or current format choice, here's an opportunity to do that. And then finally, question number 9. Approximately how many minutes of the recorded class videos did you watch during the semester? So for example, if you put 750, that means 750 minutes you watched, which would be equivalent to essentially 10 whole class periods. In total, normally for a whole semester, there would be about 1,950 minutes of questions. I'm sorry, of 1,950 minutes of videos that you could watch. So once you're done with that, just click on Submit Quiz, and then you're done. Okay. So now most of the remaining portion of this video will be me going over the rest of the logistic regression material that we have and starting multinomial regression. And what I basically done is I spliced together parts of videos of me teaching this material in the past. I've looked it all over. I've actually watched, I should say, all again, and just to make sure that indeed it all matches with what we are doing in our course this semester. And so I'm confident that it is. And so that is what's coming next.
As I mentioned, I guess last week, logistic regression, to find these betas, the beta hats, we have to use a numerical iterative procedure to try to find it. And what happens with some numerical iterative procedures, it can't find what it's looking for. Okay? It's not going to be able, in our case, to find the maximum likelihood estimates. This can happen with logistic regression. The primary reason when it does happen is when something called complete separation occurs. Now, before we get to that, first of all, let's talk a little bit more about the iterative process. Now, by default, R will use 25 iterations to try to find what these maximum likelihood estimates are. Once it hits 25 and it hasn't felt as though convergence has occurred, it will stop and say, I don't have convergence. If that happens to you, probably the first thing that you should do, try to increase the number of iterations to see if by chance this will work. And there's an argument that you can use in the GLM function called maxit to do that. So if you say maxit equal 30, it will allow you to go up to 30 iterations. But if that doesn't work, you might be left with this situation of complete separation. What that basically means is this. Your independent variables completely separate out the y equals zeros, those observations, from the y equal ones. In other words, your independent variables have perfect accuracy in predicting y equal 1, y equal 0. One group actually had that happen to them already for their project. Okay? Now, when that happens, generally speaking, R will say it can't find the maximum likelihood estimates. And I'll explain why that occurs shortly. Also, another thing that can happen, R will actually sometimes say convergence has occurred, even if you have complete separation, even though convergence actually can never occur when you have complete separation. And if you start getting messages like this, fitted probabilities numerically 0 or 1 occur. This could be, and I emphasize could be a sign that you have complete separation. What often happens when you have complete separation, what will always happen when you have complete separation, is that your pi hats will either be 0 or 1. You'll see y coming up. So when you see a message like this, then you might be starting to worry a little bit. You can actually have this without having any problems at all. It could be simply, for some independent variables, you end up getting, for your observations, pi hats are close to 0 or 1. Okay? So to help show what complete separation is in a graphical context, let's look at the following situation. Suppose I have just one variable called x, and one independent variable called x1. And when it is less than 6, y is always going to be 0. But when it's greater than 6, y will always be 1. So notice how x1 perfectly separates out the y equals 0s from the y equal 1s. It's completely separates them. So I form my data that has this situation. So I just came up with these 10 observations. I just made them up on my own. I have my x1, I have my y. And I estimate the model. And look what happens. It gets down to iteration 25. Uh-oh, we're having warning messages printed. Algorithm did not converge. Fitted probabilities, meaning our pi hats, are numerically very, very, very close to 0 or 1. You can still see what the beta hats are at your last iteration if you want to. And if you do that, and let's say plot the model, you get what's on the left side here. So I plotted the actual observations. You can see the code in my program. I plotted the actual observations, and I plotted the model using iteration 25's beta hats. Look what happens with the model. Notice how it's predicting the actual observations to have pi hats that are 0 or 1. But also take a look at the slope of this model here. Then in between where that complete separation, where that separation occurs. It's almost a vertical line. And so if I have almost a vertical line there, what's my slope approximately? Positive infinity. I'm going up. So what happens with complete separations is false. The numerical iterative procedure is going to continue increasing beta hat 1 at each step of the iteration process. And it keeps on wanting to increase it more and more and more until it gets to positive infinity. Well, it can't ever get there. And so that's why convergence didn't occur. Hopefully from an intuitive standpoint, you see, okay, I understand why that slope is so great there. Because I see how the observations are separated like that. In maximum likelihood estimation, then simply it's going to try to find this line that's right between the 2 points that are closest to one another. It's going to try to really go up as quickly as possible. Now things get a little bit more complicated. Suppose I increase my number of iterations possible. If I do that, at iteration 26, with this particular data set, R tells me I have convergence. R has actually made a mistake. How it makes a decision about convergence, if you're interested, you can take a look at my textbook on categorical data analysis. I talk about that. How it makes the decision about convergence. Unfortunately, that decision process leads to this incorrect result. So you might be thinking, uh-oh, Chris, well, what can I do? You know, sometimes I might have complete separation here. I have a problem, but I didn't actually have convergence. Of course, we don't want to use a model that doesn't have convergence because the beta hats will, if I could continue, the iterative process will continue to change. And so that's where you have to fall back on this particular situation here. Your fitted probabilities are numerically close to 0 or close to 1. Again, take a look at this plot. We can see why that should occur when you have complete separation. So when that warning message comes about, it does not mean you have complete separation, but it's a sign that that could be happening. What you could do to continue to follow up on, do I have complete separation or not? This is explained later. in this note. Take a look at your parameter estimates. Take a look at the corresponding standard errors, the square root of the estimated variance of those parameter estimates. If those are getting really, really big, that's a sign that indeed complete separation has occurred. Now, why should that matter? Well, at least with respect to the regression parameter estimates, the beta hats, hopefully that will make sense. Because if we come back to this plot here, you know, in order for pi hat, let me actually write it out. In order for pi hat to be close, very, very close to 1, or very, very close to 0, what are the beta hats going to have to be? Either very, very large or very, very small. That's why you have, let's say, large beta hats, in an absolute value manner. So you can have, let's say, negative 1,000 whatever for a beta hat, or positive 1,000. In order to get this to be close to 0, you're going to need these parameter estimates to be very large or very, very small. And so if you're seeing that happen, then you'd be thinking, and you have these warning messages pop up, you should be concerned if you have complete separation. Now, interestingly, if I were to just change two observations here, so I move this 5 to 6, I move this 6 to, 5, I get this curve, and I no longer have the curve. I no longer have complete separation. So what are some possibilities of what you can do with complete separation when it happens? There are other ways that you can estimate logistic regression models. And, we simply just don't have the time to talk about all those other methods. Complete separation occurs, but it doesn't occur that often. So that's why I don't go into the details, but here are two possibilities that you can do. One in particular, I'll just mention, you can modify the likelihood function. So we've seen the likelihood function before, and what you can do is put an additional part to it. Let's say at the very end of the log likelihood function, that actually is a penalty. It's a penalty for having, let's say, beta hats that are too large or too small, or let's say too large in absolute value. That penalty will allow you to now do reach convergence. Again, this is talked about in my categorical book if you're interested. An additional comment, well, complete separation is not necessarily a bad thing if our only goal is prediction. Because what this is saying is that you can use your independent variables to perfectly predict the y equal 1s from the y equal 0s. So in that context, that's not a bad thing. It's just you're not going to be able to state a logistic regression model because if you continue your number of iterations, your beta hats are changing. These beta hats are used for interpreting your model. So that's why that's a problem.
Now, as you've heard me probably say many times in this class, for other statistical methods that we talked about, with respect to ROC curves, there's a lot more to them than what we've actually addressed in our class. So, for example, what one could do, let me get to a nice ROC curve here. Here's one. So this is an estimate. Basically, for every sensitivity, every false positive rate, we are calculating a statistic. And so because of that, you can think that there is some true, let's say, ROC curve out there. And so what one could do is actually calculate, let's say, a confidence interval band around the ROC curve. One could do that as well. And there's a lot of other research that has been done relative to the ROC curves. We just don't have the time to discuss all of them. But I just wanted to point that out in case you found this topic interesting. There's more out there. One could also do variable selection with logistic regression. We talked about that briefly for example, with respect to discriminant analysis. One could do it for logistic regression too. The problem is that these variable selection procedures that are out there do not necessarily evaluate directly, let's say, the classification or prediction accuracy. Now, we've looked at two measures of accuracy, sensitivity and specificity. There are two other ones that can be discussed as well. They're called the positive predicted value and the negative predicted value. And they kind of look at accuracy in reverse from what we've done before. So for example, the sensitivity was the estimated probability that you predict or classify positive, or I have positive there. You can think of it positive meaning a success as well. And then actually it's a success or it's positive. You know, if you think of let's say a test, and I'm actually talking about an HIV example here. If you're testing someone for HIV, positive or negative is the two possible outcomes. Field goal kicking, or place kicking, it would be success or failure. Okay? And so that was our sensitivity. But we could turn things around, and especially for diagnosing a person with a disease, this is often very important for the patient. We can now look at the estimated probability that someone's actually positive, given that the test has said that they are positive, or that they are classified as positive. So you can see how I just flipped these two parts here to get what's called the positive predicted value. We could also look at the negative predicted value as well, where we look at the estimated probability that someone's actually negative, given that the test has said that they are negative. Well, where would this really be important? Well, let's say that you're visiting a doctor, and the doctor has run a test on you, and the doctor says that you are positive for a disease. You've tested positive. Okay. Now, the first thing that you should actually ask the doctor after that is, well, doctor, what's the PPV? What's the positive predictive value? Because we talked about how these diagnostic tests are not 100% accurate, and you would want to know what's the probability that you're truly positive for disease. And so that's positive predictive value, negative predictive value in the case of a diagnostic test. You can think of maybe an underlying logistic regression model has been used to form this information for the tests. But you can imagine other settings too that positive and negative predictive values might be important. Now, we've talked about how also there's not just one of these statistical methods that help predict groups. There's not one that is always the best. And so what's often done is that you apply a number of different methods and you look to see which method seems to work the best. And there's a number of different ways to quantify best. Obviously, overall prediction accuracy, but we talk about sensitivity, specificity. In fact, you could do the predictive values too. And in the end, you need to make a decision about which to use. And one thing that I have found to be useful in my actual applications of methods is to do a dot plot like this. And actually, this is actually a trellis plot where I look at specificity, sensitivity, and the overall for, let's say, 6 different methods that we've looked at with respect to the place kicking data set. My corresponding code here, if you want to see it, is in plotaccuracy.r. And so, for example, we can see here that in terms of overall, a logistic regression method for the place kicking data set with a cutoff probability of 0.5 is a little bit better than the rest, but not much. If you're really concerned about specificity for a particular problem, maybe we aren't so here, we can see how
linear discriminant analysis with a prior equal is best. And so this just really helps summarize what's going on rather than, let's say, looking at numbers in a table. You could do it for, this was based upon cross-validation. You could also do it for your validation data set as well. Okay, so that concludes then the logistic regression section. Okay, so we're going to talk about now multinomial regression models. Logistic regression models allow us to predict the classification or predict the groups when you only have two groups. Now multinomial allows you to have 3, 4, and so on. In fact, logistic regression is just a special case of multinomial regression. But logistic regression is used just so much. That's why I like to keep it separate from multinomial regression. And multinomial regression really takes advantage of the multinomial probability distribution. This is a probability distribution that I wouldn't be surprised some of you haven't seen before. All it is the extension of the binomial, which bi meaning 2, to now a situation where you have not just 2 possible outcomes, but 3, 4, 5, and so on outcomes. So that's why it's called multinomial. And so this is what it looks like. Suppose we have a situation where we have a variable called y that helps us denote the different possible groupings for your observations. So for example, y could be, let's say, political party affiliation in the US, where let's say y equal 1 is, let's say, Democrat, 2 Republican, and 3, we'll go Libertarian, 4 Green Party, 5, well, there's many others probably. We'll just say other. Sorry if you're affiliated with any of those other ones. And so we have 5 categories. And we might be interested in understanding better, what proportion of people are in the different categories, and eventually, what, let's say, maybe independent variables affect a person's corresponding choice for a political party. And so y is equal to j, where j is equal to 1 to capital J. So we have capital J different categories, like j equal 5. And this is what the probability distribution looks like. Let's say you sample, let's say, n people, little n people. You have n factorial over n sub j factorial, the product corresponding to all the categories. So n1 will be, let's say, the number of people who are Democrats in your sample. N2 would be the number of people who are Republicans, and so on. And then we multiply it by a product of pi sub j, which corresponds to the probability that the person's in, let's say, category 1. Pi 2's probability that they're in category 2, and so on, each raised to the corresponding n sub j power. This is the multinomial probability distribution. So let's say if I want to find, let's say I have a sample size of 10, and I want to find the probability that n1 is 3, n2 is 3, n3 is 2, n4 is 1, and 5 is 1. I could find that with this by just plugging in the corresponding values if I knew the corresponding pi's. To see that indeed that this is a special case of a binomial, consider the situation where you have capital J equal 2. So I have n factorial over, let's say, n1 factorial, n2 factorial, pi 1 raised to the n1, pi 2 raised to the n2. Now, n1 plus n2 has to be equal to n. N's the total sample size. If you only have 2 categories, that means n1 plus n2 has to be n. So because of that, I could rewrite this as, I'm running out of space here. Let's see here. N factorial over let's do it this way. n2 factorial, n minus n2 factorial. Why did I replace n1 with n minus n2? Because n1 plus n2 is equal to n. And then I have, let's say, pi 2 raised to the n2 power, 1 minus pi 2 raised to the n minus n1 power. So why did I replace pi 1 with 1 minus pi 2? Well, if everyone's just in one and only one category, that means pi 1 plus pi 2 has to be equal to 1. And so relative to what we've seen before for our binomial distribution, basically this n2 is, let's say, the number of successes. Pi 2 is the probability of success. This is the connection then between multinomial and binomial. Okay. Now let's change things up a little bit to correspond to more to what we're going to be doing. Suppose we have n, capital N, different observations of n trials. Well, how does that correspond to that political party example? Suppose I go out and sample 10 people, ask them their political party affiliation. Then I go sample another 10 people. Then I go sample maybe 20 people. Okay? Now, in this particular setting, I have 40 different people. And so n sub r here is going to be, let's say, the number of trials. Think of like in a binomial distribution. This is going to be my number of trials that I have. So 10 the first time, 10 the second time, 20 the third time. And then n sub rj represents the number of people that are in the jth category for the rth trial. I'm sorry, for the rth, let's say, implementation. Here's another example, and I should start off with this one to help explain that better. We'll go to doing place kicking again. Suppose j equal 1 corresponds to a successful place kick. Okay. J equal 2 could correspond to, let's say, a wide left place kick. So a place kick that is missed to the left. Very similar to what happened to our place kicker in the Nebraska football game on Friday when he was trying to kick the game-winning field. Well, what could have been the game-winning field goal if you were watching that game. I was there. J equal 3 could be wide right, so you're to the right of the uprights. And then j equal 4 could be, let's say, just short, which could also mean, let's say, maybe it's blocked. Okay? Now, this R here could represent a particular game of the season. So R equal 1 could be game 1, R equal 2 could be game 2, R equal 3 could be game 3, and so on. And so let's say the first game of the season, there were 3 total place kicks that are attempted. And then I observed, let's say, N11 to be 2, meaning that there were 2 successes. Let's say N12 could be 1, meaning that there was 1 wide left. N13 is equal to 0. There were no wide rights. And N14 is equal to 0, meaning there were none that were short. So that's game 1. And then game 2, you could also observe something else. So I think this is a little bit better explanation than what I was doing with the political party case. Sorry about that. So that's what our data looks like. Now let's relate this to what's called multinomial regression. So now we still have the same y. But the difference now is that these pi's, we're going to think of them as functions of independent variables. So related to the place kicking example, you would imagine, let's say, one of your independent variables, one of your x's, could be the distance to the place kick. Another variable could be, was there rain or not, and so on. Okay. So multinomial regression models are going to allow us to relate these pi sub j's, the probability of being in particular categories, to a set of independent variables. To do that, we're going to, if you remember with logistic regression, we looked at this. Log of the probability of a success divided by the probability of what ended up being a failure. So in our context, we could say the log of, let's say, pi 2 over 1 minus pi 2, where let's say pi 2 is the 2 is the success category. So we could also think of this as then the log of pi 2 divided by pi 1. Okay, is everyone following me so far? And so what we do with multinomial regression is that we extend this concept of comparing one probability to another with a ratio inside of a log. We extend it to this kind of a setting where we have what people refer to as baseline category logits. So the log of pi over 1 minus pi, we often refer to that as the logit transformation. But now we have what are called baseline category logits. What means as follows. We always take the log of pi sub little j for little j equal 2 to capital J divided by pi 1. So we're always going to make a comparison when you're comparing these probabilities to the first category. This first category is our baseline category. So that's where that name comes from. And so we always look again, log of pi sub j divided by pi sub 1. That's always going to be on the left side of our model statement. Notice if capital J was 2, how we would get equivalent to what I had just described for logistic regression. And let's say that we have just one independent variable right now to make things easy. This then becomes our multinomial regression model. Log of pi sub j divided by pi sub 1 is equal to beta sub j0 plus beta j1 times x. Notice the addition compared to what we have for logistic regression. We have that little j in there. So if you think of in the context of, let's say that capital J was equal to 3. So I have 3 categories. That means my model will look like this. Log of pi sub 2 divided by pi sub 1 is equal to beta 2, 0 plus beta 2, 1 times x. And then also I have log of pi 3 divided by pi 1 is equal to beta 3, 0 plus beta 3, 1 times x. That will be my full model if capital J was equal to 3. But notice how we have, let's say, 2 parts to it. What we will want to do is estimate these betas. These are my what are called regression parameters. Then as you will see shortly, using this model, we have a way then to estimate just pi sub 3 itself, just pi sub 2 itself, and just pi sub 1 itself. We can use those estimates for those probabilities then to figure out eventually, should I predict category 1, 2, or 3? Now you might be worried about, okay, yes? Excuse me? You mean right here? Is that what you're... Okay. It's pi 2 divided by pi 1. Excuse me? I apologize for some reason. I'm not fully following your question. Try to restate it, please.
Because the first one should be pi 2 divided by 1 minus pi 2.
No. Nope. No. We are always making a comparison to that first category, always. Now, when we were doing logistic regression, and this is what I was trying to relate to here. When we were doing logistic regression, we only had 2 categories. So that meant pi 1 was equal to 1 minus pi sub 2, because you can only be in category 1 or category 2. And so that's why I was able to do it like this there, that 1 minus pi 2. Now we have, let's say, possibly more than, well, we do have more than 2 categories. Now you might be worried about, okay, we're only comparing to category 1 all the time. Are we missing something? You know, should we maybe be comparing to always category 2 or maybe category 3? It actually doesn't matter what you use for this baseline category. The way that these models are usually expressed is so that category 1 is that comparison category. But the reason why it doesn't actually matter is as follows. Suppose you take a look at that baseline category logit for pi 2 and pi 1, and you look at it for pi 3 and pi 1, and then you do some math. So, you know, I could rewrite this as log of pi 2 minus log of pi 1 using properties of logarithms, minus then the quantity log of pi 3 minus log of pi 1. Notice I have a log of pi 1 there, log of pi 1 there. I have a negative, so that means that these cancel out, and I'm left with log of pi 2 minus log of pi 3, or equivalently, again using properties of logarithms, log of pi 2 divided by pi 3. What does that mean then in terms of our regression parameters or our independent variables? Well, we'll do exactly the same thing here. Do that same subtraction, and you're left with this. And so you can get to comparing category 3 to 2 by doing this simple subtraction. So a key thing to realize is that all we need, if we have, let's say, capital J categories, we only need J minus 1 of these, let's say, model expressions. Capital J minus 1. So if I have 3 categories, I can write out basically two, let's say, lines to my model. Of course, you could have more than one independent variable, and the extension is, I think, what you would expect. You know, here I have, let's say, capital P, not capital P, little p, different independent variables. Okay, now for what we're doing, we really want to estimate pi sub j. So let's say if I have a situation like this, and we'll call the estimate of pi 1, pi hat 1. Suppose I have a situation like this. Pi hat 1 is 0.3. Pi hat 2 is 0.2. Pi hat 3 is 0.5, and I only have 3 categories. Let's say this is for one observation. What would you predict for the category for this observation? You predict category 3 because it has the highest probability. Just like what we did with logistic regression. We predict the one with the highest probability, that category. Same thing here. You know, you could have a situation where you have something like this. Now notice that none of those pi hats are above 0.5. You might be worried. What do? Well, still, you go with the highest probability. I would predict category 3 here. And so we need to somehow reformulate our model, or, well, basically just do some algebra with our model to figure out, you know, what would pi 1 be represented as in terms of my betas and my x's? What would be pi 2 and so on? And this is how you can do it. Okay. So here's our model. Log of pi j divided by pi 1 is equal to beta j0 plus beta j1 times x. We'll just use one independent variable. I could rewrite my model as follows. To get rid of the log on the left side, I use the exponential function. So now I have pi j divided by pi 1 equal to the exponential function evaluated at beta j0 plus beta j1 times x. Then, how about I move this pi 1 over to the right side. And now I'm getting really messy here. So let me do some erasing. And so now I'm left with my model statement like this. So it's just a different way to write the model. Now, since items are going to be in one and only one category, again, we know that if I were to sum up all those pi sub j's, I should get equal to 1. Okay. So what that means then is if I have pi 1 plus pi 2 plus all the way up to, let's say, pi sub capital J, that should be equal to 1. Well, we know what pi 2 should be based upon this expression that we just got. So let's actually plug that in there. I know what capital pi sub j should be based upon that expression, so let's just plug that in there. And now look at how we only have pi 1 to deal with. So what we could do is, let's say, factor pi 1 out. 1 plus e beta 2 0 plus beta 2 1 x plus all the way down to e beta j 0 plus beta j 1 x. Let's take that stuff that's in the square brackets, move it over to the other side, and here now we have an expression for pi 1 that's only written in terms of the betas and our independent variable. So how would I estimate pi 1? Well, you estimate your model, and we'll see shortly. We're going to use maximum likelihood estimation to get our betas, beta hats. Plug those beta hats in there. Plug whatever value you have for x in there. Do the math, and you got pi hat 1. Yes?
Sorry, my questions are so simple.
That's fine.
What is 0 here, like beta j0? What does that number stand?
It's like the intercept term that you would have for a regular regression model. Okay, so if I come up here, here's where let me just erase. Oops. So that's our. It's like the intercept term. So again with logistic regression, we would have log of pi, let's say 2 over 1 minus pi 2 is equal to beta 0 plus beta 1 times x. Now we just have multiple intercept terms.
And is there any difference between multinomial and polynomial?
Well, we think of polynomials as this, like x to the 1, x to the 2, x to the 3. So that is different.
So that, yeah, my next question was why we don't have that.
Yeah. Other questions? Okay. So now that I have this way of representing pi 1, we can come back up here. Notice where pi 1 was right there. So how about we just take this expression, plug it in there for pi 1, and look what we get. We get a way to find all the other pi sub j's. So that's how we can get them. Now that I have a way to express the pi's in terms of the betas, what I can do is go back to that multinomial distribution that we saw before. And remember, I had written this out in terms of, I tried to relate it to, different football games. And, basically, this actually ends up being the likelihood function that we would use if we had, let's say, capital N different observations. And what I would do now is take each of those pi sub j's and just plug them into my expression there. Then I use a numerical iterative procedure to maximize this likelihood function as a function of the betas. And then from that, whatever betas maximize it, those are my maximum likelihood estimates. That's how it all works. We will have a function in R called multinomial that does that automatically for us. Now, this function exists in a package called NNET. That package stands for neural networks. There is just a way to make a connection between multinomial regression and what's done in another procedure called neural networks. The authors of multinomial decided to take advantage of that as a way to estimate these models. There are other functions in R that will estimate these models, but this particular function is used the most and is also in the default installation of R. So that's why I am using that here. It's not a perfect function though. If you want to know more about it, take my Static 75 course. Sorry. But it will work for us, definitely. So this is the example that we're going to look at then to see how to implement some of this stuff. This example is based upon an actual consulting problem that I once worked on. Now, I don't do a whole lot of statistical consulting, but this was one problem that I ended up working on a few years ago. And the basic background was this, is that I was a grain science researcher, and he wanted to figure out an automated way to determine the quality of the kernels, the seeds from a wheat plant. Those seeds would be used for like making flour and stuff. And there was 3 categorizations that people typically use for the quality of these kernels. Healthy, meaning that, hey, everything's good. Sprout, and you can think of that as, well, if it's a seed, it could have sprouted, just like any other seed would. If a kernel has sprouted, the quality of the flour that you're going to get from it is not as good. And so it's not as desirable as, let's say, having a healthy kernel. And then also a third categorization or third group is called scab. This corresponds to kernels that essentially exhibit some kind of disease, let's say. And again, as you might expect, a scab kernel is not good. We want healthy kernels. And so what this researcher did was let me make sure I'm not getting ahead of myself here. What he did was he had 275 kernels. And he used visual inspection on them by a human to determine were the kernels healthy, scab, or sprout. Then he put these kernels through this automated system that he created, which would automatically, without human visualization, that would automatically say, this is a healthy, this is a sprout, this is a scab. I'm sorry, let me back up. I misspoke there. He put the kernels through this automated system that would actually do some measurements on it first. Excuse me. It would measure the density of the kernel, the hardness, the size, the weight, and the moisture content. Also, these kernels could either come from hard red winter wheat, denoted as HRW, or soft red winter wheat, SRW. And then lastly here, we have what was actually the human measurement or the human decision about healthy sprout or scab. What I was trying to say before was he wants to use these variables here to predict healthy scab or sprout. And so in the end, he's hoping that his automated system could just simply take these measurements, do a very good prediction, and therefore humans don't need to be involved with making a judgment. Okay? So that's the basic setup here. The data is in wheat.csv that you can download from my website. Now, for this particular problem, we can see that we have some variables here that have categories to them. And so because of that, I want to tell R to begin with, and indeed that these are, let's say, categorical in nature. And so this is where I put then the argument strings as factors is equal to true. I don't know why I didn't double check this earlier when I was preparing for our class today, but have we seen this particular argument before? Strings as factors equal true. Okay. Sorry, I should have checked this before class. Let me explain this. So R thinks of, let's say, categorical variables. It can think of it as what R calls a factor. It's just the terminology. I know we've talked about factor analysis. It's just a totally different thing. But it thinks of these categorical variables as factors, or at least we want it to think of it as a factor. And to tell R to do that, we can say strings as factors is equal to true. If we don't do that, especially in this part of the course, R will instead treat it as what it refers to as a character variable, and some of the stuff that we do here might not work out. We need to specifically say, hey, this is like a categorical variable, so treat it as a factor in R's terminology. So that's why I have that there. Now, to complicate things here, for the entire history of R until about 4-5 years ago, this was the default. Strings as factors is equal to true. And then they decided, oh, we're going to make it false now. I really wish they wouldn't have done that. I mean, if you think of it in terms of, just software itself, you really, really need to be careful about changing the default arguments for functions that people use a lot. Because now, anytime that somebody's going to use this function, they're going to have to change all their old code to including strings as factors equal true. And so I was very disappointed about when that change came about. So, there you go. 275 observations. So, for example, first observation, the density was measured in some scale to be about 1.35. Now, whenever you get a new data set, now you start thinking, okay, let's apply some of the stuff that we did earlier this semester to it first so that we can get an understanding of it. This is multivariate data. So the very first thing is simply, I just use the summary function with the data, which is in, hold on, let me double check here. So unfortunately, I just noticed here, I have an errant 2 here. I was using this in multiple places, this data, and I made it, looks like I made a change to it. It's not going to affect anything that we do here, but just in the actual program that I have available, it's just simply called wheat. It's not wheat 2. So, we look at some very similar, very simple summary measures. So the minimum density is 0.74. The maximum was 1.65 amongst the 275 kernels. So now we can do a stars plot as well. I don't have the code here because we've seen this kind of code before. We have a stars plot. And, now we're kind of getting to the limit of, well, how many stars can I look at before it just becomes too many? And here's the stars plot here. And, we want to think about, okay, what are some things that we see here? Draw some lines. So let's focus on the pink. The pink kind of stands out. This corresponds to the type variable. The type variable is healthy, sprout, or scab. And what we see here is that basically the way that the data is organized is that we have healthy first, then we have scab, and then we have sprout. And so the pink just corresponds to the 3 different levels that we have for the type variable. Now also, and from looking at this, what you're probably doing is think about, okay, are there any of the other variables there, any of the other stars that seem to have patterns amongst these 3 different categories? And from looking at this alone here, and perhaps I'm a little bit biased because I've worked with this data, and it's easier for me to see it. But take a look at the black. The black corresponds to density. Where does it seem like I have larger densities? Amongst the healthy, scab, or sprout? Healthy, yeah. And what we'll see shortly is that indeed healthy is an important predictor of that. But I have to admit, it is a little bit difficult with this particular plot and seeing that. I think in this particular situation, I would mainly look at this plot as a way to find outliers. And I will tell you that when I first actually analyzed the data a few years ago, this was helpful because I found something that just totally stuck out from all the rest, just one observation. And I asked the grain science researcher, hey, does this make sense to you? And he says, oh, that must be wrong. And so because of that, we decided to remove that observation from our data set. And I've already removed it here. Of course, in actual application, you got to be very, very careful. You don't want to remove observations unless you absolutely think that totally must be an error. And that's what that grain science researcher told me. So we removed it. So next we can look at a parallel coordinates plot as well. So notice how I have the different categories color-coded in this plot. Again, our purpose is going to be able to is to use these variables to try to differentiate amongst scab, sprout, and healthy. What do we see from this plot? Do you think it at least might be somewhat useful? These variables, excuse me. What do you think? Yeah. So take a look at, what really sticks out is the green. Look at the lower values for density, size, and weight. Those tend to correspond to scab values. And so it makes me think, okay, I'm going to have some good success probably differentiating scab from the rest. Not necessarily going to be perfect, but I think I'm going to have some, let's say, predictive power. What do you think about healthy versus sprout, though? Yeah, it's going to be more difficult. I do see some separation. Take a look up here. We can see healthies tend to be a little bit higher density. Not all the time, but it seems like there's more healthy ones that are higher than the sprout ones for density. And so that makes me think, hey, I might be able to do something here with this. And we seem to have more reds down here for hardness. And we do have some reds up for hardness as well, but I tend to have more blacks up there. And so these are the initial looks that I like to do whenever I get a data set first.
Okay, so let's end with what's next with our class. So if you have any questions over the material, please feel free to post them to the discussion board. And while I'm at a conference, I will still be checking my email and stuff, and I'll be happy to answer your questions. Now, on Tuesday, December 2nd, the next time that we meet, we will be continuing the multinomial regression material. We will talk about project number 3 and the grading associated with it, and we will spend a lot of time reviewing for the exam. So please come prepared with questions if you have them. And then lastly here, Thursday, December 4th, then is test number 3. So that is all for today. Again, if you have any questions, please feel free to post them to the discussion board. Thank you.